So participants, now we will have the laboratory session of the NSGA3 algorithm that will be with MATLAB platform. So you have learned about the step-by-step of NSGA3 algorithm from Dr. Rachna, and now Akanksha Agrawal, our PhD scholar over here at Department of Electronics and Communication Engineering, MNIT Jaipur. She is in her final semester of the PhD and going to submit her thesis soon. She will present how to develop the code of this NSGA3 programming with the MATLAB platform. So over to you, Akanksha. You can share your screen.
Thank you, sir. I'll share my screen now. Is the screen visible?
Yes.
Is it now the MATLAB window is showing or not?
No. You can share your entire screen. Yes.
That's what I did. It is showing now, right?
Yeah.
Okay.
Yes.
Good evening, all the participants. We'll move on with the code of NSG3 that is based on the paper that you just heard about in the last session. So what Rachna ma'am explained to you was NSG, basically the major steps of NSG3. So this is the paper this entire work is based on. So here, when we talk about in last session, that was yesterday, we did the lab on NSGA2, and there we talked about the major steps of NSGA2, which started with the initialization of our problem, the cost function designing, and the declaration of the number of objectives and all that, and then it was followed by the crossover step, the mutation step, and non-dominated sorting and crowd. For the diversity measurement, the crowding distance was calculated. Now, when we talk about when the objectives, the number of objectives has increased from 2 to 3, the crowding distance does not give us a proper solution, or it might give us a proper solution up to 3 points or 3 objectives. But when we go beyond that, it does not work properly. So we have to replace that step with other steps. So those steps are basically we generate the reference points. So we have this function here, generate reference points. Then we have to normalize our population, and then we have to associate these population to the reference points. Now normalization is done because the reference points that we create are generally on the axis between between the values of 0 and 1, which are the normalized values. So instead of going for the actual values, which may vary for different fitness functions, we normalize them and we then associate these solutions with the existing reference point, and then we find out which of these solutions we need to take. So the non-dominated sorting step remains the same, but the crowding distance step is replaced by these steps. So we'll go through the major steps once, and then we'll go into the some details of these particular steps. So here the number of objectives that we are taking here is 3, and the cost function has changed to DTLZ that has 3 objectives, and it has various types of problem. Here we have taken DTLZ1. Then number of variables is kept as it is the value of x that we pass here. So it is 3 minus 1, that is 2, plus 2, that is 4. So that is the number of variables that we'd be passing for x. Then here this step, generate reference point step, is there. We'll go into the details of this step later. We'll first go through the entire code, and then we'll go to these specific points later. So again, the NSGA 2 parameters, here it should be 3 parameters. NSGA 2 it is written because it is mostly the same as NSGA 2. So the parameters here are maximum iteration, the population size, the crossover, and the mutation probability, the number of crossover solution, the number of mutation solution, mu and sigma, just like yesterday. So these remain the same. Then these parameters are for the different functions that we have created here. So these parameters would be used there. Then initialization is also essentially the same that we did yesterday, with a few added fields in the structure that we are creating here. So the position represents the solution that we are creating. Cost is for the corresponding solutions fitness values. The rank is the same. Domination set and domination count are the same. And normalized cost is obviously for after we have normalized our cost, we have we have subtracted the minimum value and divided it by the maximum. That is what normalization basically means here. And then associated ref is for the association operation, and then what is the distance to the particular associated reference point is. These are essentially the fields that we have created here. Then the initialization of the population takes place along with the first cost function calculation, and then it is followed by sort and select population, which has the steps of non-dominated sorting and association. Majorly these two steps are there in that in this function. So, and then when we go to the main loop, again the process remains the same as NSGA2. The crossover happens, then the mutation happens, then all the populations are merged, and then this sort and select population happens again. Now this is it varies from the earlier steps of non-dominated sorting, crowding distance calculation, and selection, because it combines all those three with a few added steps to correspond to the new objective functions that we have included here. So I think the major steps remains the same, except for the few that would be replacing the crowding distance calculation. So we'd go into those steps first, and then we'll run the code once and see what's happening here. So first one is this, generate reference points. So when we go into this basically gives us we'll run the code here. So here what we have is the number of objectives and the number of divisions that we are taking, and then corresponding to this it is giving us the reference points. So if we step in, m is less than 1, no. Floor of m is, if m is equal to 1, these are all the anomalies. If encountered, it should return an error, and then it actually does what it is supposed to do. So here we have a few reference points have been created here, see, and B is those reference points. So if you look here carefully, the sum of all these is 10. which was our value P. This goes on and then it returns the reference points in this step. So this ZR gives us 36 points. It is giving us 36 points, and these points, if you look at these are the normalized points, because the sum of all these points is always 1. We'll check out a few examples. Like the first point is 0, 0, 1. So obviously the sum is 1. The second is 0, 0.1 and 0.9. The sum here is also 1. Now if we go to this point, this is 0.1, 0.6 and 0.3. The sum here is also 1. So this is this corresponds to what you just studied in the previous lecture, and this is done by the technique that ma'am told you about. It is simply the division of points. The location is simply decided by this sum being 1. So we have generated our reference points. The next step that is new here is this sort and select population. This combines a few steps. So we'll move on to this step. This has major steps of normalized population, then non-dominated sorting, then associate to reference point. And then it does this non-dominated sorting again. So what is happening over here is, it is first normalizing the population. Now normalizing has 2 steps. It has to subtract the minimum value of all the fitness functions from their corresponding values, meaning that if you have function f1, function f2 and function f3. Now f1 has a minimum value among all the solutions of, let's say, 0.2. f2 has a minimum value of 0.4, let's say, and f3 has of 0. Now here, the minimum value doesn't essentially correspond to the same solution for all the fitness functions. It might vary, as in solution 1 might have the minimum value for f1, solution 7 might have the minimum value for f2, and solution 20 might have the minimum value for f3. Now we have to pick the minimum value irrespective of which solution it belongs to. So we pick those particular minimum values for each fitness function and subtract that value from each solution. So this step is called scalarizing, and then this is translation, and then we find out the maximum values. Okay, I will have to do this one again, once again. So when we step into this update ideal point gives us the minimum value, and then that value is subtracted from the cost of all the solutions. And then this step is called translation, where we subtract the minimum value. The next step for normalizing is the scalarizing, where you find out the maximum value for each fitness function, function, that fitness function, and then you divide all the FPs, that is translated outputs, by that maximum value. That is when we get our final normalized cost, which is saved here in this step. So basically it is divided by the intercept. And this is how our final cost, our final normalized cost would lie between 0 and 1 for each and every fitness function. So we'll go through this once, and see how the output is changing. If we look at the population now, the cost looks like this. Now, this is 35.49, 11.08, 162.019. Now, when we perform both these steps, let's see how the cost looks like now. Now, our normalized cost is different from our cost function. See this value 0.699, earlier it was 11.53, now it is 0.699, it was 10.83, now it is 0.52, earlier it was 110.42, now it is 0.8518. So this is how the normalization is taking place. After our population is normalized, this non-dominated sorting step remains the same as we saw yesterday. So here again, it is checking out the values of the fitness values, and based on that, it is sorting our solutions. So whichever, if it is a minimization problem, whichever has lower fitness value, it will be having a higher rank and it will be preferred over the other solutions, and also it will be called as non-dominated solution. So we won't go into this function today, as we saw this yesterday. Coming back to a sort and select population, after the normalization and the non-dominated sorting, it is going to associate our solution to the reference points that we have. So when we go to this step, okay, it has. Okay, when we go into this step, it already has ZR, which has the reference points. Then what it is doing here is calculating the perpendicular distance between these 2 points, between all the solutions and the reference points, and then it is finding the minimum distance for each solution, and then determining what what solution should go to the next iteration. So how that is done here is using this, after it calculates the distance, whichever solution has the minimum distance from any reference point, that point is selected for the next iteration if it is lying in the same let's say rank. If the solutions have the same rank, earlier in the NSGA2 we were deciding whichever solution had greater crowding distance, that was selected for the next iteration. But here, if the solution have same rank, then we check the the solutions distant from reference point, and whichever has the minimum distance, that would be going to the next iteration. Now why does that happen? Because the reference points that we have chosen are selected such that they are already lying on the plane, on the hyperplane that we have solutions on, that they are equally spaced and well distributed. They do not have the problem of either converging or diversity, since they are they have quite some space between each other, these reference points. That's why if the solution are close to these reference points, then they are obviously following diversity. Now how do you ensure that see there could be multiple solutions in the same front or of the same rank that are close to a certain reference point. Now, to avoid the problem of crowding or the solution concentrating in the same region, what we do here is we take one solution associated with one reference point at a time, and then we move on to another reference point. That is how we maintain the diversity between points. So let's say we have to select 50 solutions for our next iteration. 30 are already selected from front 1, 2, and 3. Let's say now we have to select 20 solutions out of front 4. So what we do here is, if we have here, we have generated 60, we have generated 66 reference points. So we go through each and every one of those reference points one by one, and we select a solution associated with it, which is the closest to that particular reference point. That is how we maintain the diversity between our solutions, so that no two solutions would be very close by. Now, once we are done with all our reference points, we continue with we again start with the first reference point. Let's say we have instead of 66, assume we had 20 reference points. Then we'll take for the solution for first reference point, then move on to second reference point, and so on. Say if there is a certain reference point which has no solution associated with it, then for that iteration we'll leave that reference point alone and move on to the next one. Now there might occur a case where you are done with all the reference points, but you are still short of a few solutions for your next iteration. In that case, what you do is you again go back to the reference point that you started with, that is reference point 1, 2, and so on. And that is how you make sure that you have diverse solution for your next iteration. So this is basically the change that comes in here in this NSGA3, and then we go on with the same steps. That is, we no, the non-dominated sorting is already there, and we select the solutions based on this best, whatever best fitness value they have. So the rest of the algorithm remains the same. It is just these few steps that are added or replaced. These are replacing the crowding distance basically. So after this is done, if we look at our population, after this sort and select population, let's see what happens to our population. Look at this one. So before this step is executed, we'll look at our population once. So our original population was 100. After the crossover and the mutation children are added, now our population is 200. We can even look, check that here. So our population is 200, and these all columns, that is rank, domination set, dominated count, normalized cost, associated reference, distance to associated ref, these are all blank as of now. Now, as soon as these are there for the earlier solutions which were already in the initialized population. But as soon as we perform this step, that is sort and select population, it will also select the best solution. So I think we should go into this step once and check it out, how it is changing our population. Now, normalize population, as soon as we do, see, now we have the normalized cost for all the solutions, including the children population as well. Earlier it was not there, right? So this is here. Now it will do non-dominated sorting. So we'll look at a few solutions that are lying below and see if their order is changing. So let's look at this solution 134, 0.1362, 0. We'll copy this and see where it is, if it is moving, and if it where it is moving. So this solution is number 134 here, and its cost are 7.1355, 20.2513, and 173.7106. Let's see what happens after this step. So if we again look at 134, it is again here itself, even after non-dominated sorting. But now we have the rank associated and the domination set associated with these solutions. After this, this associate to reference point step is the major step. So let's see what is happening after this is done. So now we have these columns filled as well. So these are showing which reference point this particular solution is associated with and what is its distance from that particular reference point. After this is done, again the sorting would happen on the basis of this distance. So first of all, after the sorting is done, I think the ranks would be arranged in ascending order. And when after the ranks are arranged, I think we should concentrate on distance to associated reference point along with the associated reference point. So we should have different reference points and then followed by the least distance. So let's see what happens after this arrangement is done. It is still not arranged. Okay, we'll see here associated from last run. Okay, the order is, yes, it is changed now. The rank is arranged in order and the corresponding distance should also be in ascending order. Even if it is not, here when we are selecting the solution, it should be in that way. And the top 100 solutions are selected here. So if you look at the solutions with rank 5, it'll have the solutions which have minimum distance from their corresponding reference points. Now these, if there might be other solutions which had rank 5, but they had the greater distance from their reference point, and that's why those solutions were discarded. We already saw earlier yesterday that the solutions here have to, the selection that is done here is elitist. Elitist meaning the solutions which have better diversity and better convergence, those kind of solutions are selected for the next generation. So now we'll run the entire code once and see what is happening. So here the distribution is not good right now and the solutions are not converged either. But as the iterations go on, as this goes on finding new solutions, so it goes into a better distribution of solution as well as it goes to better convergence as well. So these blue dots here are the reference points and the red star asterisk marks are the solutions. So we can see how well distributed our solutions are as compared as we have a reference point here only for checking out if the distribution is good or not. So we can see here the distribution is very good here, and the solution is also looking like it is converged with the actual solution well. So this is what is happening here. using NSGA 3. So yesterday someone asked me what is the difference between NSGA 2 and 3. So here is the answer, that in NSGA 2 you have crowding distance for calculating the diversity or for maintenance of the diversity of the solutions, but whereas in this NSGA 3, that crowding distance is replaced by a number of steps, since we cannot deal with those many objective functions with crowding distance alone. So we have to move on to a more sophisticated approach that is given here. So it has 5 steps. It finds out the reference points, then it normalizes the population or the solutions, and that normalization is done in 2 steps, that is translation and scalarizing. Translation is the subtraction of minimum value and scalarizing is division by the maximum value. Then the association to reference points is done. So all the solutions are associated with the reference points, meaning the distance of each solution is found out with each reference point, and whichever whichever reference point the solution has the minimum distance, it is associated with that reference point. Then the selection, after this association, we need to select the best solutions. So for that, the higher rank meaning better solution, as in once the first rank, the second rank, these solutions are selected, and as soon as the algorithm comes across solutions which have same rank, but we have to select only a few solutions out of those same rank solution, then it goes for the reference point associated distance. So the distance which is lower is selected first, and then it selects these points reference point by reference point, instead of selecting it only on the basis of distance. In case a reference point doesn't have any solution associated with it, then that reference point is discarded for that iteration, and the algorithm proceeds with the next reference point. And in case the algorithm is done with all the reference points and it has not yet achieved its required number of solutions for the next iteration, then it again starts with the first reference point and goes on from there by selecting new solutions. So that is what is happening here, and I think we are done with this code for today. If you have any problems, you can ask.
Participants, if you have any doubt, you can put your questions over here in the chat. The code will be shared with you. The MATLAB code of NSGA 3. So based on today's session's explanation, if you have any doubt, you can ask in the chat so that we can clarify.
There is a doubt, but it is not related.
So fine, that we will share the code. So if you will have doubt, then you can email it to us or ask us also. In there are still 2 more days are there. In any other session at the end also you can able to ask us. Okay, so thank you all. Thank you. Fine.